Okay, good afternoon, everyone, and welcome to this week's Kent Seminar Lecture. Today, we are very happy to have Professor Michael Levin as our speaker. Professor Levin is an associate professor in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota. He earned a bachelor's degree in computer science and a doctorate in civil engineering from University of Texas at Austin in 2013 and 2017, respectively. His research focuses on traffic flow and network modeling for connected autonomous vehicles and intelligent transportation systems. Everyone, please join me in welcoming Professor Levin.
Thank you, everyone. Can you see my screen?
Yes.
We can.
Awesome. Yeah, so welcome. Today I want to talk about shared automated vehicles, or specifically, how do we dispatch them to passengers? And I have a new mathematical technique, a new approach that I think has some nice properties that I'm excited to share with you that I've been working on for the past 5-ish years. So just to kind of introduce this, I think we're all familiar with transportation network companies such as Uber, Lyft, and one of the questions that they have to answer, of course, in creating their operations is, how do you dispatch vehicles to passengers, right? If you take out your phone and you call up an Uber or Lyft, how do they decide which vehicle gets dispatched to pick you up and then take you to your destination? And of course, there's a lot of dynamics here in terms of, are the drivers willing to accept their request? But with a focus on automated vehicles, we can kind of ignore the driver's side and really just look at how optimal is a dispatch algorithm. In other words, is there a lot of wasted time because the vehicle, when you request a ride, that vehicle is going to have to drive from somewhere, and a lot of that involves some empty travel to get from where it currently is to your origin location. And so you can kind of ask this question: how optimal is your dispatch algorithm in terms of what is the empty travel time, right? And we can look at that just both in the next time period. Like if we look at dispatching requests for the next 30 seconds, we can look at how optimal are we in terms of dispatching vehicles and passengers for the next 30 seconds. But we can also look at it at more of a longer term, like over 10, 20 minutes. In other words, if I request a ride and I'm kind of far away from all the other vehicles, if they dispatch a vehicle to me right away, that might involve quite a lot of empty travel. But if they wait 3-4 minutes, maybe some vehicle is going to drop off a passenger nearby, and then it'll become a lot easier to get a vehicle towards me. So we want to look at optimality not just in the short term, but also at a longer time horizon. In terms of automated vehicles, so I was in Austin over December during the winter break, and I got to ride in a Waymo car, which is really fun. There's no driver in there. They have a lot of automated systems. Basically, a car drives up, you get in, and then it takes you somewhere, which is really cool. And so that's why I'm really motivated by this topic, because clearly we're kind of getting towards the point where we have driverless transportation network companies, or driverless ride sharing. They're currently paid in San Francisco, and as I said, they're very close to expanding in Austin, plus there are some other cities that they're working on expanding for. Some of the interesting changes that might happen here is that if you don't have to pay for a driver, the cost could go down quite a bit, because a lot of the cost of having a car take you somewhere like an Uber or Lyft is actually paying that driver. And if you didn't have to pay that driver, well, you're really just paying for the operations, capital, maintenance costs of the car, which, hey, if you have a private vehicle, it's going to be about the same anyways. So it could even be cheaper than owning a personal automated vehicle, to the point where people might try to use share automated vehicles at a very large scale, replacing private vehicles on, say, home to work commutes, especially if you have a hybrid work schedule, you're only going in 2 days a week. You don't necessarily need to own your own vehicle to go to work. So this is something that I think has a very large scale potential. And that, of course, means the question of optimality becomes even more important, right? Because now we have a large number of these vehicles operating, possibly of large demand. Maybe people are more reliant on them than Uber and Lyft, and then optimality becomes really important for reducing the cost of the service and reducing waiting times. So looking at this problem, what's the best method of dispatching SAVs to passengers? You can kind of think of it as a mathematical program, if we look at the current passengers, where we say we've got a vehicle to passenger matching, we have some passengers that are waiting for rides, some vehicles that are currently available to send to passengers, and that's kind of a matching problem. We can formulate it as a integer linear program. But the problem is, as I alluded to before, it really does not look at into the future. And the problem with looking into the future is that we don't know what the future passenger demand will be. We could guess based on history. Maybe we know it's a weekday, and last weekday, like last week, we have some idea of what the passenger demand was, but we can't predict specific realizations. We can only predict averages. So there's a lot of uncertainty that we have to deal with. And so this becomes really a problem of optimizing the performance of the SAV system under uncertainty, where we have to figure out, okay, how are we going to dispatch these shared only vehicles to passengers to minimize cost or minimize waiting time or something, not just for the next minute, but for the next hour. And we could easily create a situation where maybe for the next minute, we dispatch vehicles and passengers, but then that puts us in a bad state where our vehicles are in use. And then for the next 20 minutes afterwards, we really don't have vehicles available to send to passengers. And so that would be suboptimal in the long term, even though it might be easily optimal for the next minute or so. So dealing with that uncertainty is quite hard. One way of dealing with uncertainty is formulating a problem as a Markov decision process. If you've worked with Markov decision processes, you know that the formulation it's quite doable, but the state and action space for Markov decision process can quickly grow very large. So the dimensions in the state space, where you have a different dimension for each vehicle and each passenger, that means that there are a lot of dimensions. And we have a lot of dimensions, you have a combinatorial large number of states in the process of solving a Markov decision process, which involves some kind of dynamic programming of Rayleigh iteration, some sort of iteration over states usually. It becomes computationally intractable to try to solve the Markov decision process computationally. So what I want to introduce is the idea of let's formulate this Markov decision process and then solve it analytically. So here's some background on how I want to solve this analytically and what this looks like. So this comes from back pressure control. There's been quite a lot of work in back pressure control for traffic signal timing in the past 15-ish years. Originally, back pressure control came from what they call multi-hop radio networks, which is basically internet communications or transmitting packets across the internet. And back in the 1990s, Tatsialis and Ephraimides were working on this. They formulated this problem as a Markov decision process, observed that, yeah, you can't solve it computationally, but you can create a control policy that you can prove mathematically to achieve maximum throughput. So in other words, we're not really achieving any objective here. It's not like we're minimizing the delay or minimizing travel time, but we can maximize throughput. And that's a perfectly reasonable objective and oftentimes quite useful objective to achieve. So we can develop this control. And then if we look at the introduction into transportation, that really came about by Pravin Varaya in 2013, where he proposed this, we call it max pressure or back pressure, either way, control of traffic signals. And there's been a lot of work recently on traffic signals. Now, if we look at shared all-lane vehicles, I think there are some aspects of the problem that are similar to traffic signals. So with a traffic signal, you have stochastic demand. Vehicles are entering, turning proportions, those are stochastic. You're controlling things about the network. But then again, there are also some differences where you don't, with the traffic signal, you have, kind of one-step transitions. A vehicle moves forward in space or how much they could move forward in space. And the control is one time step at a time. You decide how many vehicles you let through in the next minute or which phase you activate. Is it green for north-south, green for east-west in the next minute? So it becomes quite easy to formulate it as a Markov decision process. Let's take a little detour and look at some of the results in traffic signal timing just to motivate why you might want to do back pressure control of SAVs, and then we'll come back to that very soon. So with back pressure control in general, the way it works is you have to define a stability condition. And It could be a number of packets in the network that are, it could be a number of vehicles in the network, basically vehicles that are in the network trying to drive somewhere, haven't reached destination yet. Could be passengers in an SAV system, people who kind of enter the network, they want service, they haven't gotten service yet. And the idea of stability is that the number of passengers in the network is bounded over time on average. Now, looking at this, it's not really clear why we would care about that. So let's conceptually think about it. If we look at the number of passengers in a network, it's always going to be increasing over time as new passengers enter a network, right? Like if we look at the number of people in a network right now, 10 minutes from now, we'll have more people who want to pull out their phone, get an Uber or Lyft ride. They'll be entering the network as new passengers. So the only way to maintain boundedness of the number of passengers in the network is for passengers to also be leaving the network at the same average rate at which they enter. So in other words, entering rate must equal exiting rate for stability, which means that all passengers are served. And what we can do is prove that the back pressure control achieves this network stability whenever possible. Now, you can very obviously create scenarios, create networks, situations where it's impossible to serve everyone, right? If you have 10 people showing up, they want to ride, there's only one vehicle, you're not going to be able to serve everyone if you have 10 people showing up every minute or something. But no, neither can any other policy either. So we're talking about getting maximum throughput or achieving stability whenever some other policy would do so. So in other words, this creates a analytical comparison between the back pressure control and other dispatch policies. Um, I did some results, some numerical results on how max pressure traffic dwell time works in Hennepin County. I looked at 2 corridors, 7 intersections in total, and we used the traffic counts, 15-minute traffic counts from their engineers. And I just wanted to briefly talk about what the results look like here because we can see what we might expect to happen with shared automated vehicles. So here are the average delay results. The green indicates a decrease, the red indicates an increase. Each of these little boxes is one scenario. The rows are different intersections. There are 4 intersections shown here, and the columns are different time periods, so like AM peak, PM peak, off peaks. So you can see that with most scenarios, most intersections and most times a day, we can find some parameters for max pressure control to give us a improvement in delay. Now, all these different boxes for each, these different null numbers, those are different parameters we tried, different cycle lengths, different time steps, etc. Things that can vary. But a point here is we can get some nice delay reductions compared to the current actuated coordinate traffic signals, and we can get them fairly consistently. Some of these numbers are over 50%, showing very high delay reductions. Okay, so that's one corridor. Here's the other corridor. You get the idea, right? We have a very large delay reductions. So why does this happen when we have a back pressure control that's really supposed to maximize throughput? Well, if you have a fixed demand coming into the network, like a fixed number of vehicles coming into this corridor, and you increase the throughput, what really happens is that people get through the corridor faster. So what we see is the throughput can't really go up because there's a limited number of people entering, but the time it takes for people to get through can decrease because of the extra efficiency from back pressure. All right, so let's focus on shared automated vehicles. And I would say this is mathematically, I mean, it's hopefully conceptually easy to see why we would want to do back pressure control, having this Markov decision process focusing on uncertainty. But actually achieving back pressure control mathematically is not super easy. And so there are a couple of different approaches that I'm going to talk about. I'll start with the first approach that I came up with, and then I'll kind of go through some extensions of what you could do there. So to start off, we kind of saw before that we needed to have a stability definition, right? To get the maximum throughput, we need to show the network remains stable. In other words, the queues of something like passengers probably remain bounded over time. So the natural choice here is to pick a queuing model that looks as the number of passengers that are waiting for travel. So if we look at people who pull out their phone, they're requesting a travel, they haven't yet been picked up, we're going to keep track of how many people there are. And we'll keep track of them per origin destination because when you dispatch a vehicle, you really care about where their origin is to pick them up, where the destination is in terms of getting the vehicle to take them there has an impact on where the vehicle will end up or be available after that trip and how long that trip will last. So looking at this, the number of waiting passengers, we're going to have quite a simple conservation model. If we look at a number of waiting passengers at time t plus 1, we can calculate based on the waiting passengers at time t by adding the entering demand, which is going to be assumed to be a IID, random variable. And then we're going to subtract how many vehicles drive through that node and can pick up passengers. Now, vehicles could drive through because they're making an empty trip to go somewhere else, right? So there's this minimum here, which is how many people are waiting versus how many vehicles are driving up that could pick someone up. And what we want to get stability is for the number of waiting passengers in the network to be bounded on average. And so this is the long run average. Take time horizon going to infinity, look at the average number of passengers waiting in the network over that time period. In other words, as we saw before, this only works, or this condition only holds if the rate of new customers is the rate of served customers. So looking at that variable y here that kind of defines the vehicle movements, we need to expand on that as well, because so far we've tracked the waiting passengers, but the vehicle movements, of course, determines what we can serve. So the way of doing this is create a similar state evolution model. So you want to look at how many SAVs are on link J at time t plus 1 that have an origin R destination S to keep track of where they're going. And that's, again, a conservation law, just looking at how many vehicles are there, plus however many vehicles enter, minus however many vehicles leave. The idea being that this J and the Y, I to J, which like link I to link J, kind of tell you route choice as well as dispatch. Now, whether that's a good idea for the model, there are different options that don't really have this route choice embedded, but that's one way of doing this. We also have a state with the parked SAVs, number of vehicles that are parked and available at node R, and those are going to be related to some extent to departing vehicles. So this is again a conservation law. If you look at parked vehicles at time t plus 1, it's the parked vehicles time t plus any vehicles that arrived minus vehicles that are left. And if we look at all this, the dispatch policy becomes this sort of model predictive control. It's an integer program where we're trying to decide the future, well, current and future shared automated vehicle movements. And those are determined by this V, which is passenger service. And we also have this F variable, which is the movements or kind of flows of SAVs. The W here is an input, that's the number of waiting passengers, that's what we observe. But to get stability, we have to look kind of into the future and consider a time horizon. If we just look at the current time step, we don't really get stability because we're not anticipating the future enough. So we have to look far enough ahead into the future to kind of balance the extra capacity of the fleet with the uncertainty in passengers. The main point here is this theorem right now, which is trying to show stability. So that, in other words, or formally, we want to prove that if there exists a SAV dispatch policy that can serve all customers, whatever it may be, then the back pressure policy also serves all customers. And this is not just a talking about a deterministic number of customers. This is talking about the average variable number of customers with some expected value that's known, but the distribution is not known. The way we prove this is by defining this set D or script D. And the point of this set capital D is that it's going to be the set of all average demand rates that can be served. So it might be called the stable region. It's a set of demands that could be stabilized by some dispatch policy. So if we look at this theorem, here's kind of how we might summarize this capital D term or set. if we have a demand rate, an average demand rate that's not in the set capital D, it's impossible for any dispatch policy to serve all customers. On the other hand, we also prove that if the average demand rate D is in the interior of the stable region capital D, then the back pressure policy serves all customers. There's this kind of boundary issue where the Markov chain basically becomes null recurrent, and you can't prove stability there because it would take an infinitely long time to return. But that's a boundary condition. It's not unlikely to happen that the number of customers is exactly equal to that value. So practically speaking, this is pretty close to getting maximum throughput, and this is what prior work on back pressure control is used. Proving it, I don't want to go through that. It's a Lie optimal function. It gets really ugly in algebra. The point here is that we can do that. So here's some numerical results that kind of illustrate what stability might look like. So we took just the Sioux Falls network and generated some demand. The nodes here marked in orange are nodes that we created an asymmetric demand to make things interesting. So we picked those nodes to have higher demand than normal. On the right, you see the average unserved queue length. So the gray bar shows a demand rate that's not in a stable region. It's not stable. You can see that the number of passengers waiting grows over time. In practical terms, what this means is you pull out your phone to get an Uber or Lyft or a Waymo, and the waiting time is very high and increasing as well. Whereas like maybe if I tried to get a ride now, the waiting time is 20 minutes. If I wait 5 minutes later and try to get a ride, the waiting time might be 30 minutes because it's increasing over time. Number of passengers is increasing, you can't serve them all. On the other hand, the orange line shows what it looks like when it's stable, where the number of waiting passengers will increase and then it'll kind of stabilize at some constant value. And this is normal. It's just based on the time it takes to get a vehicle to the passenger. There are always going to be some people waiting. Okay, so that's the main idea. I want to talk about a few extensions, things we can do with this to make it more interesting. So the first is kind of handling the situation of preemptive rebalancing. In other words, instead of waiting for a passenger to arrive, can we send the vehicles to places where we think they'll be needed, where we think there'll be passengers, and yet still have the stability or the maximum throughput properties of the back pressure control? And the answer here is yes, definitely. We have to change the objective function of the policy. And the reason you have to change this is that that objective function, or what this pressure term, it really comes from getting this proof of maximum throughput to work. And if we change the model behavior, say we add preemptive rebalancing, then we have to change our objective function as well. But other than that, it becomes a very similar kind of Markov evolution model. We don't have to conceptually, the math can get ugly, but it's conceptually very similar. So I want to show, instead of going through another set of equations that are more complicated and yet conceptually very similar, I kind of want to show what this might look like. So we can look at different variations of parameters. So one of the parameters we're looking at the x-axis is a fleet size. How many vehicles, how many SAVs do we have available to serve passengers? So you can see we're looking at very large fleet size numbers. We're looking at 14,000 to 20,000 vehicles SAVs, and we're solving this problem for that. We're also looking at this parameter k, which kind of determines how much we want to rebalance the vehicles. So you can imagine if we try to rebalance vehicles very aggressively, we run into the issue where maybe the time that we spend rebalancing vehicles is actually going to increase quite a lot. We're going to spend quite a lot of time moving vehicles around, and it may or may not be useful right away because you move a vehicle somewhere, it doesn't mean that a passenger is going to be right there. It just means the vehicle is closer. So what you can see on the left graph is the average dispatch pickup time. So as we more aggressively try to preemptively rebalance vehicles, that average dispatch time decreases, but it doesn't, it's going to decrease, but there's a limit here. So you can see the k is equal to 10, k equal to 15 lines kind of overlap, because at some point you're just starting to move vehicles around rather than being and getting an useful relocation for them. Um, and you can see on the right-hand side that as that k increases, we spend quite a lot more time moving vehicles around. If k is 0, that's no rebalancing case at all, so that's 0 time rebalancing. But as we get up to k equal 10 or 15, we spend quite a lot of time moving vehicles around. Um, Here's what this looks like on the Winnipeg network. We can look at this on a lot of networks, but it's clear that there's some benefits here. The point here about this preemptive rebalancing is that we also compared it with a different paper just to see how this worked, and you can see that the max time is sometimes better. It depends on what the fleet size is. Sometimes it's close, but sometimes a little worse as well. But we're doing comparably to other dispatch policies, and I think the explicit consideration of stochasticity in our model is quite helpful there. So if we saw variations in passenger demand and we have a lot of stochasticity, a high variance, we can handle that probably better than some of the other policies that exist that aren't looking at the uncertainty, but just looking at dispatching vehicles for the current situation. Another variation here is if we have customers with that leave the system with high waiting times. So in other words, if you try to request a vehicle and you're waiting a long time, you're not going to just keep waiting. You're going to give up and find some alternative, like instead of Waymo, you use Uber or Lyft or something like that. Because if we look at a back pressure control previously, it definitely, I mean, our waiting time was not super high, but there was also no guarantee that it wouldn't be very high for certain customers. You might have like one origin that's far away, and then the waiting time for that customer is very high. So we created a model where we're trying to see like what can we do if we look at customers that are leaving the network, and you can kind of get a similar dispatch policy idea. It's not, it gets a little bit messier, but you can kind of get a similar back pressure where instead of looking at the number of vehicles in network, we look at how many people have left. Um, that's more of a trying to deal with practical issues than really exploring the concept too much. So what I want to do is more focus on the concept and talk about maybe an alternative queuing model that might be more useful. And I think I find it more useful. I also find it easier to work with. And here's the alternative. So if we look at this first back pressure control, what we're doing is maximizing this objective. And we look at this objective, it's number of waiting passengers, the W, times V, which is vehicle pickups. So in other words, we have to wait for W to increase for the vehicle pickups to happen. So if the W is small, like 1 or 2 passengers, we don't have a lot of pressure to pick up passengers there. The other downside of this is that the network math here, I mean, I didn't go through it all, but it's very complex and difficult to work out, and I spent quite a lot of time trying to figure it out. So here's an alternative, and instead of tracking the number of waiting customers, let's track the waiting time of the longest waiting customer at that node. So some of the advantages are if there's only one customer, the pressure to pick someone up could still be very high because as that one customer's waiting time increases, as they're not picked up, then that pressure would also increase. But how does that affect our maximum throughput results? So to prove maximum throughput, we need a stability condition. And the equivalent stability condition here is that the network is stable if the average waiting time of the longest waiting customer is bounded. And it ends up being a kind of a very similar intuitive concept where if that waiting time is going to infinity means that you're not serving passengers because people are entering the network over continuously over time. So I didn't come up with this at first. This was by Saif Jabari, but I've kind of adopted it as well as I think this is a better approach. So here's kind of the idea is I end up with a Markov chain evolution that's quite complicated. We're trying to look at the head of line waiting time at t+1, and it has multiple cases. It's based on a head of line time at time t, but it could, if you have a customer that's picked up, then the head of line waiting customer is now someone else, and so their waiting time is decreased. Plus, you have the case of what happens if a passenger arrives, what happens if not. So there are various cases here that are kind of all encoded into this complicated equation. The point is not to learn the equation, just kind of to show the concept exists here. Um, so we only show is this head of line waiting time is a Markov chain model. It involves the head of line time at t plus 1 is based on the head of line time at t. Um, we have a model for the SAVs being assigned to the certain paths. And the reason I'm doing this by assigning it to paths is because this model actually, I've generalized it so that we could consider SAVs that are electric or that are ride sharing, picking up two customers and then dropping them off instead of doing one at a time. And so we can generalize this with a assignment of SUVs to paths instead of um, to individual customers. Um, and then what we end up having is called this minimum drift plus penalty policy. It's basically back pressure except with a different objective. So, so I've already called it MDPP. But the idea here is that there's a pressure associated with passenger service, and that pressure is based on the passenger or the waiting time. There's a cost associated with vehicle service time and rebalancing that if you move vehicles around, it has some cost to it. But if passengers have been waiting a long time, that will exceed the vehicle service time or the rebalancing costs, and it will therefore prioritize passengers. So one way of intuitively thinking of it is that you might be located far away from all the vehicles, but if you've been waiting long enough, there's a very high pressure to serve you. And so that's why I think this is more useful because practically speaking, we want to serve people who have been waiting for a long time. Um, we can end up with we can add pantry rebalancing to this as well, and we can look at maximum throughput properties. The proof again is a little bit complicated, but you still have the same basic idea. We define some stable region, which is the set of arrival rates that can be served. If our average arrival rate is not in the stable region, you can't serve all customers. If it is in the interior of the stable region, then the back pressure will serve all customers. We can get some performance bounds on this on average waiting time. There's a lot of equations here just based on how they were derived. Point here is we can create a bound on average passenger waiting time and average SUV service time, and those might be useful things to have. Um, so the last kind of topic I want to look at, though, is what we might do in terms of using this, what we've developed. Because so far, all I've really been talking about is back pressure as an operational concept of how do we dispatch vehicles to passengers with the goal of maximizing throughput. But there is a separate concept, which is looking at the stable region, which describes the average rates of customers that can be served by a given SAV fleet and operations. And on the flip side of the operational problem is the strategic problem, which is answering questions such as how large of a fleet do we want to have? Where do we want to put charging stations if we have electric SAVs? And those questions can be answered by looking at the stable region because the stable region equations tell us which passengers can be served. So going back to the proof of maximum throughput, we observed that there were two main things we could show, which is that first, if our average arrival rates are in some stable region set, here it's capital lambda, then the network can't is unstable for every dispatch policy. There's no dispatch policy that can serve this. And the second is that if the average arrival rates are in the interior stable region, then we can stabilize them guaranteed by the back pressure policy. So in other words, you might think of let's try to optimize around this stable region. If we know what our average passenger rates are going to be, why not design the infrastructure so that we ensure that the stable region includes our forecasted average passenger rates? And I want to kind of highlight that the paper I wrote in part B, it looks at this as a very generic, general maximum throughput control policy. In other words, instead of being focused on one specific SAVs, I considered variations of SAV services like electric vehicles, ride sharing, even first last mile integration with public transit. So this concept here of the trying to use a stable region to optimize things, it works very much in general. So looking at the stable region, we can describe it in terms of certain equations. First is a conservation law that says where are SAVs going? If we look at the average SAV trips per hour into some node R, that's also a average number of trips per hour leaving node R. Practically speaking, in a minute by minute, you don't need a conservation, but if we look at the hour at an hour long period, we're going to have conservation. We also need to serve all demand, and there's also a limit on how much travel time we can achieve with an SAV fleet. So if we have a fleet of, say, 10 vehicles, that means that they can spend 1 hour of time traveling every hour of passenger service. And we can figure out how much time we spend per passenger on average. So average travel time would have to be less than the fleet size. Here's a graph showing the stable region that's calculated versus the stable region from a simulation. And you see the simulation has in blue, which is a little bit less than the calculated simulation stable region. One caveat here is that it's when you get close to that boundary of the stable region, it actually becomes very difficult to detect whether it's stable or not, just because of the stochasticity involved. So this this gap that you're seeing, it could be that the simulation is different, but it could also just be that it's hard to detect, and so I erred on the side of caution there. But regardless, the point here is that the calculated stable region is a pretty good approximation of the simulated stable region minus maybe some percent gap, like 5% or something that we need just to maintain service. So here's kind of the idea of designing a SAV service for achieving that minimum level of throughput that we need to serve everyone, is that we have our stable region equations as constraints, and their objective might be minimize cost. Cost could be number of vehicles purchased, it could be charging station infrastructure, or it could be whatever you want in terms of trying to maintain level of service. So in a recent paper that I just got accepted, I used this to optimize charging station locations for electric SAVs. But there are a lot of different ways you could try to use this concept. Okay, so I'm kind of like a little bit over time, but I'm just going to talk about some conclusions here. So main conclusions is this concept of maximum throughput dispatch of shared online vehicles and passengers under uncertainty and future demand. And that under uncertainty part, I think, is really important because it's very difficult to deal with uncertainty. And most prior work kind of used maybe a deterministic approximation where you just assume that entering passengers will be certain rates or a focus on the passengers that are currently there without considering the uncertainty in the future. There are two different ways of modeling the queue to achieve maximum throughput, either looking at passenger waiting time or number of waiting passengers, and several practical extensions of behaviors we want, like preemptive rebalancing or passengers leaving the systems if the waiting time is too high. A lot of future work that I think could be useful, especially where we see Waymo and other shared online vehicle systems being pushed onto actual roads now. This is a very timely problem to work on. So some of the future work here is just numerically, how does maximum throughput control work against alternatives? I mean, we have this mathematical proof that says it should achieve maximum throughput, but does that translate to lower waiting times for passengers? And practically speaking, if we look at an alternative, it doesn't mean that some alternative won't find maximum throughput as well. So we'd have to compare numerically to see, are we doing better? And there really hasn't, there's been a few studies numerical that includes numerical results, but not really that many. There are various other things like optimal balancing policy, doing non-constant travel times, all their uncertainty that we could look at. But the main one is trying to extend this to practical systems, I think would be valuable. So I want to give a thank you to a graduate student, Toshu, and my undergraduate students, Jake, Robinolt, Maria Sharanowski, who helped with the math and the results here. And thank you for attending. So I'm happy to take questions.
Thank you, Professor Levin, for the presentation. We'll take questions from the room. Yes.
Hello, hi, Michael. Thank you for the presentation. I enjoyed it very much. Just a quick question. This is very interesting, but I'm wondering about the throughput. And then basically you are using throughput as sort of the stability criteria. But then do you consider a possibility of multiple equilibrium, even under the same operating policy, under the same demand, under the same fleet? The system might have multiple equilibria, and then such that the wild goose chase might exist. And then does your policy or does your control, which is operational real-time control, really distinguish these different equilibria? And also, do you see what I'm trying to say? That the user experience can be very different, even if the throughput is the same. Am I making sense? I don't know.
Yeah, I think I understand. Yeah, and I agree with your insight that there are multiple, I wouldn't call it equilibrium. There are multiple solutions that have maximum throughput. Some of them might be better than others in terms of like waiting time or other things. And the answer really is no, that the math isn't, we can't optimize an objective. We can show that the policy maximizes throughput, but that's one of the limitations of solving the problem analytically rather than computationally, is we're not optimizing for an objective. So there are tricks we could do to try to steer the policy towards one of those solutions on that boundary of maximum throughput. But it's not the same thing as guarantee. But on the flip side, I think if we look at alternative policies, there's not really a guarantee of maximum throughput or any optimality under uncertainty either. So it's kind of like a trade-off.
Yeah, can I follow up just really quickly? So you had shown this stability region. That was a question I had from the beginning on the planning side, right? We want to know what's the minimum fleet we need to serve a certain demand, or what demand we can serve with a certain fleet, right? Then you had this simulation versus yeah. I was wondering actually whether that could be the wild goose chase, that actually when you are doing simulation, you can see that with the same demand, the fleet size from the simulation is larger than your model prediction maybe, or calculated, right? If you draw a horizontal line. Then could it be because of the, like, inefficient equilibrium that may exist, or you call other solutions that may exist?
Well, I don't think it's so much due to an efficient equilibrium, just because mathematically it's proven to maximize throughput. So I don't think there's so much inefficiency that we can lose here. But I think one thing we are seeing is that when we look at anytime we prove this, there's kind of this idea that if the arrival rates are outside of the stable region, you can't stabilize. But if they're in the interior of the stable region, then you do see stability. And practically speaking, the interior could be a very small difference, like 0.01%. But if I'm trying to detect that with a simulation, I'm not going to run this simulation for over like 10 hours and wait to see if it's stable. I want to see if it's stable over like 1 or 2 hours, or a shorter time period. So I think that's why you see this gap here, is partly just that it's difficult to detect stability, and practically speaking, you probably want to achieve that stable behavior sooner. Like if I look at kind of the stability, you can see that up to time 10,000 seconds for this particular model, we have increasing average number of passengers. And then after that, the stable demand kind of levels off. But 10,000 seconds is a long time to wait to get there, right? So we would like to see that stabilizing sooner.
Thank you.
Any other questions? Yes, John.
Thank you so much, Professor, for the presentation. And I had a question about the variable that you were considering for optimization, because in your results, you consider in the QA criteria either the waiting time or the number of passengers that are waiting for a service. But when you consider this, does the optimization of vehicle use happens as a consequence, or that could also be a variable that could be included here?
Yeah, I think so. Looking at this, the optimization problem is it seems like maybe like there might be some intuition there, but there really is not an intuition or a conceptual model for this optimization problem. The way this is derived is we want to get maximum throughput, and there's a very specific form of the optimization problem that makes the proof of maximum throughput work. So we can kind of look at this and say, like, yeah, there's a concept of high waiting times or other things to optimization, but there's only so much you can do to change it or improve it without losing that maximum throughput.
I may have a follow-up. You also presented other ideas that could be useful for parser optimization in future research. And are all of these variables mutually independent, or can they be put together maybe to try to reach an ideal optimization for all of these factors?
You're talking about like trying to optimize the fleet size or infrastructure?
Yeah.
Stable. Yeah. Well, there are definitely some constraints that relate to these. Like, for instance, the vehicle travel is related to demand and then bounded by the fleet size available. But other than that, it's kind of free, I think.
Thank you so much.
Of course.
Questions? If there are no more questions, thank you, Professor Levin, for joining us and for the great presentation. Everyone, please join me in thanking Professor.
Well, thank you for attending. I appreciate it.
Thank you.